Hello everyone, welcome to this talk, Prospects and Processing for Cubic Silicon Carbide Power Devices. This is part of the Silicon Carbide in Europe workshop. It's a pleasure for me to be here, so thank you very much. And I should say that the work I present here was really done by my partners in the Challenge project, which is a Horizon 2020 Cubic Silicon Carbide device project, the material and device project, I should say. So these are contents of the talk. First of all, I will introduce the material and properties. We'll talk about the advantage, the Mos advantage for cubic silicon carbide. So that's the second item on the agenda. Then we'll discuss the breakdown voltage, arrive at some closed form solutions for depletion width, breakdown voltage as a function of doping for cubic silicon carbide, and discuss some applications. Then we'll present some of the results from the Challenge project, specifically in terms of ion implantation, and finally I'll summarize the results. So here we see the material properties of cubic silicon carbide pitted against many of the other conventional semiconductors, right? Silicon, 4H silicon carbide, GaN, and so forth. We can see the band gap is around 2.36 electron volts, which lies somewhere in between 4H silicon carbide and silicon, okay? Cubic silicon carbide is based on a hexagonal bilayer structure, all right? So it repeats after 3 layers. So we have these, layer A, coined layer A, B, and C, which are different stacking arrangements of the hexagonal bilayers. These repeat after these 3 particular positions. That's what the 3 denotes. And then we end up with a cubic structure shown here. And if you want more information about the materials, I recommend talking to Professor Francesco Lavia from CNR in Catania in Sicily. So anyway, if we look at the properties, all right, we have the wide band gap gives rise to many other advantageous properties, specifically intrinsic carrier concentration. Again, it lies in between silicon and 4H silicon carbide. It's around 0.15, all right, per centimeter cube. This gives rise to high temperature capability, all right? Not as good as 4H silicon carbide, probably better than gallium nitride, because don't forget gallium nitride, although it's got a lower carrier concentration, intrinsic carrier concentration, is typically formed over silicon wafers in a heteroepitaxy arrangement. And silicon has a very high intrinsic carrier concentration in comparison, which means that it's very difficult for this material system to operate beyond about 200 to 250 degrees. Okay, we also have a reasonable bulk mobility of 800 centimeters squared per volt second. That means that unipolar devices have a reasonable resistance value. We have an electric field half that of 4H silicon carbide, all right, but pretty much 10 times that of silicon. So, again, we can support higher voltages than silicon, not quite as high as 4H silicon carbide. Probably compares to gallium nitride again, because although the gallium nitride critical field is much higher, again, the limit is when you put it on silicon, okay? Saturation velocity, 2.5 to the power of 10 to the power of 7. And crucially, the thermal conductivity is also comparable, it's comparable to 4H silicon carbide, certainly much better than silicon. Gives us high temperature, again, the possibility to operate in harsh environment, high temperatures. But the real benefit, one of the major benefits for cubic silicon carbide is the oxide, the Mos interface, okay? And here you see that the band offset with silicon dioxide is the highest, it's 3.7 electron volts for cubic silicon carbide, higher than its silicon, 6H silicon carbide, and 4H silicon carbide counterpart, all right? And what we see is that, for a given tunneling of current into the semiconductor from the oxide, all right, if we look at the 4H system, which is kind of, the commercial silicon carbide power material, 4H silicon carbide SiO2 system, the electric field is 1.5 times higher than the silicon system, but it's 2.25 times higher than cubic silicon carbide system, right? And this has real advantages and real positive prospects for cubic silicon carbide in terms of reliable power electronics. All right, and I recommend this talk. By Dr. Fan Lee, who elaborates on this theory in his presentation and shows some real results from challenge. Okay, if we look again, another introductory slide. Okay, we look at the interface trap density. This is the conduction band edge. The x-axis is energy. This is the conduction band edge for cubic silicon carbide. There are no traps, no interface traps around or near the conduction band edge for cubic silicon carbide. In contrast to its 4H counterpart, where we see here we have a lot of NITs, near interface traps, right? So cubic silicon carbide is free from interface traps, and you know, it's still troubled by these pi bonded carbon clusters, but the traps are the real killers, and we have, you know, it should be a much cleaner, low resistive Mos interface. And if I would recommend this reference here, you know, this is to read this reference here. This is where this diagram is taken from. This plot is taken from. Okay, so what we can do if we analyze the impact ionization coefficients and come up with a fit for the impact ionization coefficients with the electric field is we can use the impact ionization integral, okay, and insert that fit. We find it's around 2 times 10 to the power of 40 times the electric field to the power of 7. We can put that fit into this ionization integral, solve for a triangular approximated electric field, all right, which is, you know, the classic non-punch through design, if you like, and we can arrive at the closed form solution, all right, for the breakdown voltage and depletion width as a function of doping. And we can see that for like 1 kilovolt, we can get reasonably, you know, approaching 1E16 doping concentration, and around, you know, a 10 micron, just over 10 microns of drift layer, epi layer required for that kind of voltage rating. A real exciting aspect of cubic silicon carbide, from my perspective, is the positive prospects for cubic silicon carbide trench devices. All right, here on the left hand side of the slide we see a trench power MOSFET. All right, and what happens is that the electric field within the semiconductor underneath this trench, because this trench is etched into the drift layer, transfers into the oxide. All right, and the law, it follows Gauss's law, which is given here. All right. So this is Gauss's law, and what we find is that for 4H silicon carbide, which is the black one here, you can just see it along this kind of trajectory. You know, the 4H silicon carbide, the oxide, okay, for a trench power MOSFET in 4H silicon carbide is much higher than for its cubic silicon carbide counterpart. All right. Now, you might be wondering why the 4H silicon carbide critical electric field strength here is given as 4, because you know, in the previous table we said it was 3.3 or 2 to 3. But don't forget, the critical field is also a function of doping, which is given down here. All right, and obviously for lower voltage devices, we can dope the drift layer much higher. Therefore, the critical field is also higher. All right. So, you know, for these lower voltage devices, and this is where we're kind of operating in terms of cubic silicon carbide, right, up to about 1,000 volts. There's a real advantage here for 3C silicon carbide in that the field mitigation in the oxide is a lot lower than it is for the requirements, I should say, for field mitigation in the oxide for cubic silicon carbide are a lot lower than they would be for 4H silicon carbide, right? This is a typical field profile taken from the Balaga textbook. All right, and basically what the message we're trying to portray here, or the message I'm trying to get across, at least, is that for you know, for a trench power MOSFET, okay, the electric field in the oxide will be much lower for cubic silicon carbide than it will be for 4H. Therefore, the device intervention in terms of, you know, specific designs to mitigate that field, you still do need to mitigate it, because you need to get it down to about 3 megavolts per centimeter. But the clever things that we need to implement in the device are less stringent for cubic silicon carbide than for 4H silicon carbide. So again, this improved reliability for trench power MOSFETs, and a real prospect, you know, it's a real, we've got a real chance of making trench MOSFETs work in cubic silicon carbide. Again, going back to the unipolar limit for cubic silicon carbide and plotting out all of these kind of commercial devices around that unipolar limit. All right, we see here that you know, cubic silicon carbide should, you know, follow the trajectory between about 800 and 1,000 volts, and this is where it can really, if you look at the unipolar limit here, we do have these 4H silicon carbide devices which are beyond effectively the cubic silicon carbide limit, all right, according to this plot at least. However, this doesn't take into account reliability, for instance, right? So we are really comparing the devices within this 800 volts to 1,000 volt range, all right? And, you know, this is taken again from Balaguer's textbook. That's typically, you know, motor control, right? We're talking about electric drives, propulsion systems for electric vehicles, for instance, or industrial drives, right? Lower power industrial drives, but still. So now we talk about some of the results from challenge, all right? We've done 2 types of ion implantation, and we're talking about accepted dopants here, okay, P-type implantation. We've done them at room temperature on cubic silicon carbide on silicon, so 3C silicon carbide epitaxy on silicon. All right, and we've also performed them on bulk, which I'll talk about in a second. However, we are constrained in this system. We're constrained by the melting temperature of the silicon. All right, we can't go above 1400 for sure. And what we've done here is we've implanted at room temperature, okay, aluminium. Okay, and you can read these conditions. These are the conditions of the implantation, and then we've characterized those using this electrochemical CV, capacitance voltage measurement, and scanning capacitance microscopy. All right, and what we find really is that it's very difficult to characterize, because making an ohmic contact, especially on, you know, moderately doped semiconductor ion implantation concentrations is quite difficult, right? And it was because of that we found it very difficult to extract some ohmic contact values. All right, now we can see from this as ion implanted simulation profile, okay, maybe that's SIMS, and then we do electrical chemical CV. We see that for lower doping concentrations, okay, we get a reasonable activation level, all right, here. And, you know, we can see that the presence of the PN junction was only really detected after a 1390 degrees C anneal for 4 hours, all right, and using a carbon cap sample. So another trick we did was to use a laser annealing system. The main this allows us to anneal the silicon carbide layer without the temperature transferring into the silicon layer, all right? And this was done on a 600 degrees C implant, you know, implant temperature. These are the main parameters, okay, for the laser anneal. And on the right-hand side here, we see some results, all right? We can see that this is the surface, the substrate temperature as a function of time. For this particular case, it's 1,000, the laser fluence is 1,000 megavolts per centimeter squared, megajoules, I should say, per centimeter squared. And you can see this profile, okay, for the temperature profile of the silicon carbide, right? And it doesn't affect the silicon lattice. It doesn't get through to the silicon lattice, because you can see here that same profile is a function of depth, all right, rather than time. And we can see that, you know, we're nowhere near the silicon layer, because don't forget, silicon carbide epi layer is about 10 microns wide. All right, here we see some we've done some laser annealing and analyzed the ohmic contacts and sheet resistivity. All right, so we've got on this sample here, we have some van der Pau structures and some TLM structures. All right, and here are the conditions. But crucially, what we find is that this 1000 millijoules per centimeter squared fluence seems to be the optimum condition for forming ohmic contacts, all right? And we've achieved ohmic contacts below 10 to the power minus 2 specific contact resistivity, below that value for that condition. And when we look at the sheet resistance, which we extract from the Van der Pau structures, we can see consistency for a shot value of 52. So we pulse, we shoot the laser a number of times at a specific location on the wafer, 52 times in this case, and we see a consistent sheet resistance. Whereas when we increase the number of shots, okay, the resistance seems to increase with implanted dose, all right? And finally, we've done some bulk cubic silicon carbide analysis at 600 degrees C as well, all right? So you can see the conditions. We went for a typical box profile here, all right? And what we find when we do, the background doping, I should say, of the N-type epi layer is 1E16, all right, 1E16 per centimeter cubed. And what we find here is that we get much better ohmic contacts because we can anneal at much higher temperatures, all right? So we've annealed here at 1700 degrees C, which we couldn't do with the previous system because we had silicon underneath, all right? So this is much more versatile and, much more akin to a real power device, a real silicon carbide process, as in 4H. So here we see specific contact resistivities of around 10 to the power of 3, 10 to the minus 3, 10 to the minus 2 ohm centimeter squared. Okay, they're not the best, but they're a lot better than the previous example on the heteroepitaxy where we had to anneal for a very long time. Okay, and again the sheet resistance about 2.5 kilo ohm per square. So in summary, okay, cubic silicon carbide has a potential to be much more reliable, especially the MOS system, than 4H silicon carbide, that's for sure. We think that the range will fall between 800 volts and 1000 volts for this material. Studies have demonstrated that we've shown that we've managed to activate P-type acceptors into using ion implantation in cubic silicon carbide epi wafers, all right, heteroepitaxy in this case. We've also demonstrated quite a novel laser annealing technique to achieve localized annealing without affecting the silicon wafer underneath. And we've got pretty good contact resistances, less than 10 to the power minus 2 ohm centimeter squared. And but the bulk shows most promise, okay, because we can anneal at much higher temperatures for shorter periods. Okay, this is still 2 hours, but the potential is there to increase that again and do maybe a few minutes anneal potentially. And we've got lower contact resistivities, 10 to the power minus 3 to the power minus 2 ohm centimeter squared on implanted on P-type implanted bulk, okay? And we see typical PN junction behavior here as well. So I should acknowledge, thank you very much, everybody. I should acknowledge Francesco, who's really leading this project, done a brilliant job at leading us. And this work is not my work, okay? The ion implantation was done by IBS, or Frank. I'm not sure what his photograph is. There he is, it's Frank from IBS. We have also Fabrizio Roccaforte, Roberto Nepoti, who's really instrumental in the implantation stuff, okay, really helped us a lot. We have the guys from Warwick as well, okay, so Fan Lee, whose talk's coming up later. You should definitely check that out, definitely check it out. And we have Rosica Yakimova, Adolf Schroner. Anvil have unfortunately dropped out of the consortium, but I should say this is not my work, this is everybody's work, okay? So thank you very much, and thanks for Funding Challenge, and thank you for my fellowship through the Royal Academy of Engineering. So that's it. Thank you very much.